Defined Receivers, or SDRs. Why? There are multiple reasons, but primary among them for the amateur are 1. Low cost. 2. The ability to be configured for a wide range of frequencies. 3. Wide bandwidth is easily obtained. 4. Direct conversion into the digital realm, where a computer can do most of the hard work of measuring and applying calibrations to the input. New Elec has several SDRs that are based upon the popular TV dongles from the Far East. They have souped them up with SMA connectors, which are more common, replaced the clock with a 0.5 part per million clock, and an aluminum enclosure to minimize noise generated by the electronics. They have a frequency range of about 25 megahertz to about 1.7 gigahertz. Costing between $30 and $40, these are extremely affordable to get started in radio astronomy. That said, they have an 8-bit digitizer and are limited to about 3 megahertz of bandwidth around whatever frequency you are observing at. There are other issues with this SDR, but they revolve around using multiple receivers at the same time. The AirSpy SDR is an interesting SDR for radio astronomy. It has a 12-bit ADC, operates from 23 megahertz to 1.7 gigahertz, and has 10 megahertz bandwidth. It also has several programmable pins for controlling equipment, as well as an input port so that it can run off of a standard clock, such as one synchronized to GPS signals. It has an issue with the internal clock causing a spike at 1420 megahertz, which is very annoying for hydrogen line work, but it is manageable. Coming in at about $170, this is a very good SDR to get started with. This SDR is the basis of the SARA Raster 4 project. It has a frequency range of 100 kilohertz to 3.8 gigahertz and up to 60 megahertz bandwidth with a 12-bit ADC. While only $299, this is without a case. Adding a case for it currently bumps the price to about $600. The thought is that for more than a few optical astronomers, they will spend this much or more for a single eyepiece for their telescope. In those terms, this is an eyepiece that can handle almost anything that you can get into as an amateur radio astronomer. These and many other SDRs are available. Like optical astronomy, you can spend as much as you want to. SDRs need to be programmed, and probably the most common way is to use the software put out by the GNU Radio Group. They support a number of different transmitters and receivers. Putting together a receiver is as simple as dragging boxes onto a screen. Draw the connection between the boxes and setting a few parameters. This has made GNU Radio a core piece to any SDR usage, and its use in radio astronomy is no exception. Shown is a sample sketch to perform pulsar reception. In addition to GNU Radio, there's a software community to help make sense of all the data in radio astronomy. While many packages have been ported from the professional realm, such as Tempo used to detect pulsars, more than a few have been developed within the community. On the commercial side, some, such as Jim Sky, have a presence and publish some of their works at very reasonable prices for people to buy and use. Some of Mr. Sky's utilities include Radio Eyes, which is a star chart program which represents the sky in the radio realm rather than optical. Another is Radio SkyPipe, which is a computer version of a script chart recorder. It is used by many and is key to SuperSyd and Radio Jove. Radio SkyPipe is used by many other fields. Mr. Sky also has some software available for free. There are many other software projects as well. Search github.com and you will find a few hundred projects listed for radio astronomy. If you cannot set up an antenna to observe for yourself, there are other opportunities such as helping with the many hardware and software projects out there. Is light pollution an issue? The good news is that radio astronomy does not have any issues with light pollution. In fact, you can observe 24 hours a day. The bad news is that you need a relatively electrically quiet area to set up your observatory. Electronic noise pollution, or RFI, is possibly an even greater problem than light pollution. What is RFI? Just as you would talk to your neighbors about a poorly designed outdoor light, you may have to spend some time tracking down bad power line insulators, nearby electric fences with bad insulators, arcing motors, noisy LED lamps. While a problem, these are all issues that are actually easier to address than bad lighting. The FCC is your friend, as RFI is a finable offense, and the FCC is serious about controlling it. Large companies are quick to comply rather than pay fees. In the case of arcing motors or noisy LED lamps, these are items that are often a problem for the owner. The noise may be interfering with their TV or radio reception and is often an indicator of early failure. They may actually thank you for tracking down that troublesome problem. These issues are all solvable and therefore should not prevent you from getting started. There are also a lot of resources from fellow enthusiasts to help you find and solve these issues. If you go to the SARA website, you can find how to determine whether your site is suitable, as well as suggestions on tracking down interference. The projects previously mentioned, Itty Bitty, SuperSID, Radio Jove, meteor detection, and hydrogen line are all possible for most people. They are easy to do and relatively cheap. Getting fresh materials for each of these 5 projects should cost under $1,000. None of these projects is much over $200. Most are under $100. None of these projects is too challenging, and if you look at the forum on the SARA website, you will find plenty of help. Some final thoughts from Mrs. Burnell before the ending. If we assume we've arrived, we stop searching, we stop developing. Thank you for your time. I hope I've given you the basic information to start thinking about radio astronomy as a hobby. If you go to the SARA website and click on the education menu, you can get a lot of good information. Additionally, there's a lot of information on the Radio Jove site.
Okay, that's the end of the presentation. In our testing and the like, we thought that we were getting the sound directly from the video, but apparently it's coming through the mic. So I apologize for the echoes and dubious sound quality. Although you have to take at least some of that sound quality issue as being the speaker. I'm going to move the people back onto the first screen, so I'm actually looking into the camera now. Let's see here. I will stop. There we go. Stop sharing. Okay. Thank you for the compliments. The question is, what can I do to improve the presentation? I'm always looking for comments. Okay, are there many schools doing this? If you mean observing, the answer is yes. SARA has sent out a number of Radio Jove and SuperSID presentations, and they have provided data for most of them. I know that some of the kits go out and we never hear from the people again, but the majority of them, vast majority, actually do get, we do get information back from. There we go. Okay. Like to see more comments on meteor scatter. Okay. I will see about adding that into the slide deck. Yes, I'll have to make sure and go through the slides, make sure that I've got the URLs on the slides correctly.
Hey, Ed, go ahead and read the question off because they're not necessarily on chat. They can't see the question.
Oh, Okay, let's see here. The first one was, are many schools doing this? And I'm assuming the using either SuperSID or Radio Jove, and as I said, the answer is yes. More comments on meteor scatter. Yes, there needs to be more. That I need to make sure I have web addresses on the slide. Yes, I need to make sure to do that. Perhaps students' work could be posted on the SARA site. I'm not entirely sure what you mean by that. For the two projects, that research is sent directly to Stanford, or I think it's NASA. I'm not sure where the collection point is, but the information is gathered and processed by the groups. A suggestion for the video: add video data taken in real time of hydrogen 1 and red shifting data. Very dramatic experience. Yeah, I think I saw that presentation recently. Someone had done that somewhere, but I don't have a reference for that. I'll have to go and look that up and see if I can make it fit. Now, just a comment here. You got to hear the quick version of my presentation that I normally give at SARA. My presentation at Green Bank normally takes over an hour, partly due to interaction with the people who are there, but mostly due to the fact that on the whole, I take a lot of breaks in talking. I don't have the best set of lungs in the world, so that becomes a bit of a issue. Let's see. Itty Bitty can detect the moon and phases with a better sat finder. Yes, that is true. But for what is provided, you can't, or described in the Itty Bitty discussion. Now, one of the things that I've been playing with here recently has been Itty Bitty and an RTL SDR, one of the cheap SDRs, and and unfortunately, I haven't had enough time to actually work with that any. I wanted to see if that would be a better starting point for people who maybe have seen a soldering iron but are not too familiar and really don't want to go in to hack up a meter that they had just bought. Are many schools using the video? I honestly don't know how many copies have been distributed. And for the life of me, I'm blanking out on the educational outreach director's name here. I apologize. I'm just terrible with names, but I'm sure that there are this is the other reason my presentations at Green Bank stall out, is I just start stumbling over my tongue there. Let's see. They're graphs, but if going to NASA, okay. I'm assuming that's about the SuperSID graphs, and what actually is sent in on those is the data that is actually collected from the receiver that gets collected by radio SkyPipe and uploaded to a FTP server for the people to pull down and start processing. So they don't actually send any graphs. I'm not sure if there's a different question there, so I apologize. Let's see, KM4ZIA and KM4BUN are glued to the presentation. Thanks. Okay. Thank you for the compliment. SAT finders are all over the place in ability. Yes, that is true, which is why if you go look up itty bitty, they recommend using a specific version of the SAT finder. And with that finder, as I said, detecting the moon is a bit dubious. It may be possible, but with other ones, but the point of the one that's described is that you modify it slightly so that you can get an audio output to feed into your computer for graphing with Radio SkyPipe. Let's see. No other questions at this point. I guess my two questions are standing aside from these comments, which I'll save and keep, and any others that come in. Did I meander too far off of the track of my presentation? Did I cover anything with too much detail for an introduction? Did I go through and not give enough? And obviously, meteor scatter is one of those that I'll have to add a little more information in on there. I think I'd taken those slides out, which was a mistake because I didn't have a good description for it at the time. So I'll work on its description and add that back in. Okay.
Great, Ed. An outstanding pitch. I like the way you were fielding the questions on chat. We might make that the way to do it because I think it worked very well. So for the rest of the presenters, bring your chat up and just monitor that. We'll do that. I mean, you can go through that after the thing. So Ed, outstanding brief. Thank you very much.
Thank you.
And
thank everyone else.
It went very well. We've got a few minutes based on the schedule. We'll have Charles Osborne come on up. He's queuing up now. Now we got a lot more people online than we did before. I'm going to go over a few other basics. And by the way, this is Rich Russell, your moderator for today. Everybody, it looks like we got audio and everything up okay. Presenters, I guess there's a way, Ed did have a problem that it looked like he was getting the audio through his speakers or through his mic instead of direct. There's a button on the side in sharing to, I think, do that. Stay muted unless you want to talk. We're going to try to communicate through chat. If you're going to chat with an individual person, do it in the private mode. We're going to try to have the chat as the questions for the presenter, and then he's going to go through that, or I will cut in and because I'm monitoring chat too, and I'll maybe stop him and ask a question. Other than that, we're going to have a 5-minute question and answer session after the talk, depending on how much time we got left. Then we'll, so feel free to put some questions in chat and then we'll try to get them to the speaker. The voting, we still have voting going on for the conference, well, not for the conference, but for the election this year. We're going to extend the deadline to send it to Bruce, who's the treasurer or the secretary, till 9 o'clock tomorrow morning Eastern. That's so he has time in the morning to compile all the answers and get the results to us in the afternoon when we start tomorrow's session. You need to email that. Everybody got an email on the with the ballot on it, and so go vote in your ballot and email it back to Bruce. by 9 o'clock Eastern tomorrow morning. Drake's Lounge, we will have Drake's Lounge again this evening. Basically, we'll have a moderator, and you guys will go through it. Last but not least, let me see. I'm going to make sure I'm not cutting into Charles's time here. I'm going to show you the door prizes. And let me make sure I get that here. Okay. Okay, so door prizes. This is Charles Yarborough from rfconsultant.com has donated a TPI 1005 Moderator. All right, we're going to have 3 SARA shirts, and you know, 1 per winner. And the caveat on these guys is there's like 3 colors, and they only have small, medium, and large, no extra larges and stuff like that. So before you accept this, now each one, when we have a random number generator against your number on the on how you guys all logged in, or not logged in, but how you guys all registered. So we'll run the random number generator, and then whoever's number comes up wins, and then you need to pick a prize. 1 mouse pad, SARA Mouse Pad, a Radio Astronomy by John Krause, a must-to-have on your bookshelf as an amateur radio astronomer. 2 SARA memberships, or should I 3 SARA memberships for the next year. 1 Super SID, so that's the full thing, including cables and everything, antenna, sound cards if you need it, etc. Jim Sky runs Radio Sky Publishing, has got 2 licenses. So if you win, you get 1 license for 1 of the products, is the way it works. You just need to tell us what product it is, and then we'll get you the license. I'm saying this is the Drake's Lounge. So we've had a pretty good Drake's Lounge participation. I recommend we're sending out the notices for Drake's Lounge. It'll be monthly. This is a chance to have a very good interaction with everybody in the club, which is 300 people or so. A lot of expert talent there. So I recommend everybody log in on Drake's Lounges. Okay, this is how I'll show this screen when we have the raffle, and basically it'll say how many of the items are left. If a star is covering it up, that means it's already been taken. And I do recommend, specifically about the generator, if you're not capable of using it, don't take it. Only because the you know, we just don't, you know, we don't want it to be wasted and stuff like that. So if you think you can handle that, all the other ones look like they're you know, even for the you know, the 10-year-olds and things like that can use those. Okay, stop. Okay, so our next speaker, Charles Osborne, retired last year after 40 years experience in military and commercial satellite communication systems engineering, antenna range instrumentation design, and including 8 years as technical director of Radio and Optical Astronomy Observatory. Last year, he gave an excellent presentation on going to Arecibo, so I welcome Charles. He's been a longtime SARA member. Take it away, Charles.
Okay, can everybody hear me?
Yes.
Okay. Let's see, how do we switch over to my screen, or are we?
Go to share on the bottom.
Because I'm just seeing you.
Alt S also works.
Okay. All right. Are we,
I see you.
you're seeing the screen there?
Yep.
All
And
right.
and we
There
hear
we go.
you. There you go.
And we got full screen. Okay. How's the audio?
Great.
Good. I was afraid the fan noise and things would bother me. Okay. This is a beginner's session. This has always been a good follow-on to Ed's talk. Some of the biggest problems with, I think, with radio astronomy is the variety of things that you can get into. So my key points I wanted to make is for people to not get overwhelmed by all this. But I find a lot of people jump in and then they don't get the data that they were expecting. And so I wanted to make a few key points to keep people kind of calibrated to what to expect. First, we're going to go through these each individually. Radio astronomy signals are much weaker than anticipated. This is something that, and all these things are just kind of observations that I've made along the years. And gain drift in the electronics looks just like the signals we're trying to receive. Very many times you'll think you've got something and then you'll just realize it's a change in temperature. So modern technology, laptops, Wi-Fi, smartphones, satellites, GPS, all that adds spurious and noise. So we're immersed in problems that we have to solve to really do radio astronomy. Learning basic astronomy so you know where you're pointed at all times is a key thing. Precision time is another aspect of all this that is good to know. Precision time is vital to making sense of the data and sharing the results. Start out simple is a really key point. Set realistic goals and then work up from there by refining and improving. Build on others' work. Don't try to be a master of all things. Okay, going to the first one. Radio astronomy signals are much weaker than anticipated. Begin by developing realistic expectations of what you'll see. At 1420, the signals are weak even on large antennas. A 10-foot dish might only see the sun as a few dB change. Most other signals like CAS-A, the moon, Cygnus, will be fractions of a dB. And we kind of have a list that's, let's call it the top 10. And you kind of need to start at the top, make sure you can receive the sun and that you're getting, the signals you expect, and then work down from that and refine your equipment performance. Everything's about temperature. You'll get tired of hearing Kelvin used in so many different ways in radio astronomy. It's just pervasive, and you have to sort of learn what to expect in context. Kelvin can be used in noise figure, talking about the signal change, and it's just physical temperature as well. Basically, we're measuring energy changes. Everything about radio astronomy is relating them to the RF energy created by a resistor heated to some degree Kelvin. At room temperature, 290 Kelvin is minus 174 dBm per hertz. That's a good number to memorize. That one allows you to do some calculations in your head once you've got that number memorized. Noise figure is the noise added by the receiver's electronics. Noise also measured in equivalent Kelvin. And I made the comment here from some of the presentations that I've done, that I had a spiral noise calculator, and I didn't include it in this presentation because it's probably copyrighted or something, but it was in the back of a vendor catalog that I had one time. It's just a very clever way to take a long nomograph and spiral it into a single page. And so I had copied of some of those and handed them out at the at Green Bank. Okay, gain drift in the electronics looks just like the signals we're looking for. That's kind of a problem because most people jump into observing with a lot of anticipation and label every peak as astronomical in origin. In fact, I would say the best place to start in radio astronomy once you've built up your system, whether it's an RTL, SDR, or whatever, is by placing a 50 ohm termination on the LNA input. In other words, make it so that it only sees the noise from that 50 ohm load. And then if you still see fluctuations, you've got work to do in stabilizing the system. You can start by putting everything you can away from the sun's heat and inside thermally controlled boxes. Shield the receive electronics from home heating vents, and also RFI. RFI will show up in some of the measurements too, from Wi-Fi and things if you're not careful, or even cell phones. So that's just a good place to start, because you'll be looking at the sky and you'll think, wow, what's that periodic every 30 minutes hump that comes up and then goes down? You'll eventually realize that it's your home heating system turning on and off, and a slow temperature change causes a gain drift in the system. One thing that's used almost universally in radio astronomy is calibration noise sources. They inject a certain amount of noise into the system, and you can calibrate your system based on the amount of change that you see. So that's a very important thing, is to have everything calibrated, and that way if you accidentally change something or the gain changes, coax, one of the most insidious things is getting water in the coax, and that noise source will help show that your system has changed sensitivity, and you can then do some troubleshooting to figure out why. So a lot of times people will just change a setting accidentally, and they'll think they proclaim that they've made an improvement in system performance. Let's see here. And I don't have chat up. I got to figure out how to do that in case somebody's sending questions. Richard, if you see a good question come through, let me know. Okay, let's see. Scale is critical. Everything we do, it's good to calibrate everything in a way that you can remember, take a lot of notes. Without it, you won't even know if something has died in the chain, water in the coax, and all that. Dead parts thermal noise looks disturbingly like working system noise. Going back to a known source to compare past measurements will show the difference. People who skip this step usually end up taking meticulous data of wasp nests in their feed or water-filled coax. So I couldn't stress that enough. Take good notes, make it a habit. Years later, it can be the difference between realizing you witnessed something that you can add your data to, or just gibberish that gets ignored. A lot of the professional data sets start with a header called a FITS file format. And it basically elaborates on the exact location, things about whether the antenna was tracking, where it was pointing, bandwidths, things like that, that if someone else is looking at your data 10 years later, they can at least have a good idea of what you were doing and if it might be usable to compare their data to. Okay, the next topic, modern technology. Like I said, we're surrounded by laptops, Wi-Fi, smartphones, satellites, GPS signals. XM Sirius is another strong one. Satellite radio that all that is extremely powerful in terms of watts per square foot onto the earth. So you want to be sure you've got a fairly clean environment so that you don't claim you found a pulsar or Jupiter S-burst only to discover it's your neighbor's lawnmower ignition noise. There's a lot of stuff out there. Radar from a nearby airport, for instance, will throw a big burst into 1420 measurements every 5 or 6 seconds as the radar goes around. So things like that, you have to be aware of your environment, sort of run some listening tests before you dig into it too far. And since the RF is ubiquitous in our world, people oftentimes will be searching for the problem when it's funny to watch them find out they're wearing it, as in a cell phone. And I have done tests where, I'm looking with a spectrum analyzer, I'm trying to find what's the strongest interferer. And I was amazed at how strong laptops' Wi-Fi transmitters are. And so things like that put out a lot more RF than you might think. And so it can, even if it's not on the same frequency, it can sometimes cause problems, descents to the front ends and so forth. Gain compression looks a lot like noise coming and going from a distant frequency. Airplane traffic. In one situation, I was watching a certain direction with the dish at the house, and I kept getting strong interference. And I figured out finally that if I walked outside, I would see an airplane generally going through the direction of the antenna that the antenna was pointed at. And so that was reflecting some strong 1295 megahertz radar into the receiver. Okay, let's see. Yeah, filtering is important to learn about. Most of the time we try to avoid putting any loss in front of the LNA, but having a filter to protect an LNA is very important if you do have these problems. Most of us don't live in quiet zones, and it's very difficult to keep these things from being an ongoing problem if you don't have a good filter. So sometimes the filter will be all the difference between making sensitive measurements and not. And also, you could just learn to recognize the periodicity of the interference and comment it out of the data it corrupts. A lot of the large observatories like Arecibo have just had to automate this kind of thing because they couldn't get all the radars that were in range from bothering them. So they just couldn't filter it out, so they just had to comment it out of the data. That way it doesn't bias the measurement, and it has to recover slowly from the energy that it puts into the reading. Okay, and this is just some interference pictures from one of the locations I lived in, Duluth, Georgia, showing the amount of clocks from laptops and neighbors with cell phones and laptops and Ethernet, things like that. So there's quite a bit of interference and just general ups and downs in the noise floor. Leakage from cable TV systems, for instance. All it takes is one F connector that's loose to turn the outside of a coax into an antenna, and you'll get a lot of interference generated across the band that is normally constrained to the coax. It'll just transmit it. Okay, another good point, I think, is learn basic astronomy so you know where you're pointed at all times. Simple programs on the cell phone even, where you can point it up at the sky and start to identify things in the sky at night and begin to get a feel for right ascension, declination, how things are located and move in the sky. Of course, we do radio astronomy day and night, so in the daytime you don't have you don't see the object, or at least the area of the sky to work with it and know what you're looking at. So it's a little harder in the day, except for when you're doing the sun, where you can watch the shadow of the sun move the feed shadow into the center of the dish, and you know you're pointed right then. But you got to compare that with what your dish actually reads for azimuth and elevation, and calibrate all that. Local sidereal time, it's a good thing to begin to have a feel for how your exact position on the Earth changes what azimuth and elevation you're going to see the object at, and all these time conversions, universal time and local sidereal time, and local time, standard time gets to be second nature once you use them a lot, and you'll start to figure it out. Just double check your understanding using these programs. Do some tests on the moon, sun, and a few key constellations, and it gives you a good way to figure out if you're off by an hour due to daylight savings time. Every time we go through daylight savings time, you get into a question of whether your software has corrected, and then another piece of software takes that time and runs it into the program and corrects again, so you're off by 2 hours or not off at all. So it has you'll typically at that time of the year need to go through and double check everything just to be sure that all the programs corrected the right amount. Okay, it's also a good way to find due south. Got magnetic declination changes and things that affect what a compass says. So if you use an astronomy program, or even just use the astronomy program to predict when the sun is going to be due south, you could go out there and do the shadow trick where you wait for that exact time and then draw a line down the shadow, and that'll give you due south. And then use a dish, same way and record the peak power and when it occurred, because it doesn't necessarily mean that your dish is pointed exactly where the shadow indicates, the shadow of the feed on the center of the dish, because if the focal point is not exactly where you think it is, the dish is a little bent or something, your pattern may be changed so that the your basically the beam of your antenna will probably end up having a little distortion. And actually, when you do the test and you record your data, you'll actually see that in the plot of the sun. Instead of having a nice build up and then drop down, it'll be a little distorted, and so that'll be an indication that your feed is a little off, not in the exact focal point. Let's see. Okay, and then pointing at other angles and other times to try to make sure you've got the east-west baseline and everything lined up also. And make sure your watch is set within a minute of correct for most cases, but it's good to be sure of your time when you're doing these measurements, because they will affect the angle measurements if you don't have it set very close. Okay, finding the North Star to double check your compass assumptions is a good idea. But due south seems to be key, because that's the direction that gives you the ability to see the lowest in declination. For most of us in North America, that is going to mean that you'll be looking due south to be able to see closest to a galactic center, and that's a nice bright radio source. But at high latitudes, you may see tree thermal noise or ground noise first, making it more difficult. And also side lobes. If you're not focused too well, the side lobes of the dish will also get larger. And instead of being maybe 18 or 20 dB down, they might be higher. And so that will see the thermal noise as you get closer to low angles. So things like that, it's good to kind of create your own tests of your quality of your focal point alignment on the dish. There's even a trick with putting little pieces of mirror on the dish and having it reflect little dots of light up onto the feed. Is another trick that I've done, where you can find out where that focal point is. I mean, you can do it mathematically, but it's just an interesting way to do it. Take a sheet of paper and move it back out of the front of the feed back towards the feed, or even with the feed not in the dish. And you can actually, when you're pointing at the sun directly, get all those dots of little pieces of mirror scattered around the dish to focus on the actual focal point. Okay, precision time is vital to making sense of the data and sharing the results. GPS time is a little more pervasive now, and it helps us get at least within a few seconds of correct, and also has helped a lot with the frequency errors and things. So we end up with a lot of us are using GPS references on the frequency. It's not, you don't have to do that as a beginner, but certainly it's good getting the system clocked to internet time, if nothing else. And the receiver, of course, if you've got a handheld receiver, that gives you some degree of portability when you're outside doing these kind of test and want to know the exact time and latitude and longitude and things to go into the measurement. Okay, all this adds validity to your data. If everyone did it religiously, we'd have a much better record of solar flares, meteor bursts, gamma ray burst transients, or interference to compare with each other. Take good notes of all the things about your measurement, your antenna LNA, frequency, receiver bandwidth, noise temperatures, all the system settings that you can change. And, you know, think of this, like I said, as if you're going to put it in a time capsule or something, look at it in 10 years. What would you want to know rather than trust in your memory? And what was the intended target? Was the antenna fixed or tracking? Local conditions, even weather, is good to write down and add into the data. If it was raining, temperature, sunny, how much wind was there? Because wind will at times cause the dish or antenna to move a little, and that could show up in the measurements. So make all these things, you know, kind of a habit of taking good notes. It's an engineering kind of a thing to always sign and date everything. So this is just an extreme of that. Okay, and probably for the beginner side of things, most important, start out simple and set realistic goals, and then work and refine and improve and build on others' work. You generally find that the people that have the most success start with Radio Jove or Super SID, learn the basics of data taking and astronomy, and they've got a good chance of accomplishing the goal. Others who buy a 16-foot dish, a lot of electronics, tracking motors, FFT processors, LNAs, and computer equipment, and only get to see a small bump on a graph after much effort, well, they typically sell it all or just switch hobbies. It's almost exactly the analogy of the beginning optical astronomer buying a 16-inch Meade telescope and observatory dome as their first telescope. It's a little too much, and people have always told me in optical astronomy, the best telescope is the one that you'll use. And so if you buy something that's so complicated, you'll avoid going to all the trouble of setting it up and using it. So you want something that practically runs itself, and you don't have to worry about very much. You just turn it on or even make measurements over periods of days or weeks, and it automatically takes the data. And I think a good success-oriented path to bigger and better things for most people seems to be to get the basic astronomy knowledge first, get a Radio Jove or Super SID, do some solar and Jupiter observing, then get into maybe a drift scan of hydrogen line with something like an 8-foot satellite dish, screen mesh, lightweight dish. Larger tracking dish for weaker sources or different bands maybe would be a next step, but really getting much above 10 or 12 feet, the difficulties go up exponentially with the size of the antenna. So 8 foot is a good size. In fact, I've got a 7 foot that I can pick up with one hand. The surface of the dish is on a nice, real light aluminum frame that holds the shape, and I could pick up the whole 7-foot dish without the backing mount in one hand. It's so light. So that was a good starting point without getting totally involved in welding up a mount and pouring concrete, things like that. And then some go into the SETI hunt at this point with larger dishes and things. Another one is a molecular line receiver. That's kind of an advanced topic, going for hydroxyl, methanol, or formaldehyde. And interferometry is also kind of an advanced area, but it's another one that is possible. There's a lot of tricky things in there that you really need to read up on and do some single dish work first before you jump into interferometry. So start out simple. And I guess you want to do something that you can, the results, what they're going to be, and then verify that you actually see what you have predicted. Meteor scatter, I don't think I don't know if I can get this to come through, but I did have a recording of a meteor ping here. Let's see if there's an audio. All right. Computer audio. Let's see. What's that like? Yeah, I'm not sure I can get that. I may have to just put that on the website or something to let people play that. But anyway, I've got a meteor ping here recording, and this is a picture of a meteor that Janice and I took.
Charles, just go ahead and hit your button there. See if you get it to play.
Okay.
Yep, I hear it.
You hear it. Good. Okay. All right.
Try it a couple more times.
Okay, this is meteor. And so you're basically looking at the reflected signal as the meteor ionization changes. You can see how it changes colors, goes through different brightness. And this graph is also of a meteor storm, a meteor shower, where you can see lots of different meteors and how the signals vary during the shower. So this is fun to watch, so you can see if you're in the peak of the shower or not. Okay, this is just a picture of a dish that I have. This is my project. It's a carbon fiber dish. It's handy in that it is made to be transportable. So this one uses these octagon-shaped boxes to actually package the dish, and then when you get where it's going to be set up, the boxes act as counterweights and back feet to allow the dish to be stable. So I can actually put the dish surface together standing on these boxes and rotating it around different angles. So each one of these little gores of the dish have snaps on the back right here, which allow it to lock into the adjacent panel. So this was kind of a neat one that got surplused out where I was working. Somebody stole some of the parts off of it for repairing a similar dish, not realizing that the company that made the motor controller had been sold. And so when they went back to that company and said, we'd like to order another one of these, they said, well, we don't make that anymore, and it'll be $100,000 to gear up the engineering crew to replicate that. So it sat in the stockroom for a few years, and they finally scrapped it out, and I was the person who ended up getting that. So, and
Hey,
yeah.
I'm sorry. I have one question on chat from the last slide. What frequency was the meteor captured?
That one, I think it was from one of the television channels, maybe. It was something that was a CW signal, in other words, continuous tone. And so you're looking at the Doppler shift is why the tone changes. So that was where some of that change in tone happened.
I think that's somewhere around 55 megahertz range.
Yeah. But all that kind of thing changed over time as they've taken television channels off and went digital. I mean, one of the most fun frequencies to use is FM because of the you end up with you can actually hear the station for a second or two. I mean, it's very unusual to actually be able to get the station ID at the right time so that you hear that. And of course, in ham radio, if you're doing it, there's a lot of the Joe Taylor WSJT modes where you're actually working two-way via meteor scatter, and so that's kind of neat because you get actual readout of how many dB down the signal is, and you can see the where you're talking to because you're actually talking to somebody on the other end. But anyway, that meteor scatter is kind of a fun area. Okay, another comment, don't try to be a master of all things. We're not all mathematicians, programmers, astrophysicists, or microwave electrical engineers. Don't be discouraged if you run into stumbling points. Get help so you can keep going and continuing to learn about the areas you are curious about. Or skip some that you are not likely to enjoy learning and just buy that part. Or trade your expertise with someone who needs a complementary skill. Some of our most advanced members have teamed with others to do more than either could have alone. Continuous improvement, I would say, is the ideal path to enlightenment.
Hi, Charles. 5-minute warning.
Good. Okay. Okay. If you're looking for fame and fortune, keep looking. Most of us started out in optical astronomy, wowed by Hubble pictures or Astronomy Magazine, colorful, awe-inspiring Photoshop masterpieces. Radio astronomy is none of that. It's a lot like watching a chart recorder or a seismometer. You're unlikely to get an ooh or an ah out of your coworkers for showing them a bump on a graph. But if you explain that that bump comes from 26,000 light years away and you built all the electronics to receive it yourself, you might get a wow. But from a spouse, generally you best consider it a success if you get a "that's nice, dear" out of it. To the non-scientific majority, what we do is pretty close to stamp collecting and excitement. But you can always look to other SARA members for a pat on the back. Paraphrasing John Kennedy, we don't do this because it's easy, we do this because it's hard. Okay, questions? And I don't have the chat up. How do I get the chat up on this particular Do I unshare the screen?
You can go to the view options on top, and it should have a chat option up there.
I don't see view options.
Go to the top of your
It's
screen
actually on the bottom of the screen.
or the bottom, depending on which one you got.
It's coming off the top.
I think Alt H will also do it.
Okay. Okay. All that did was.
All right, I'll go ahead and read it. I guess you just got one.
Okay.
Good comments, Charles. The DST clock change problem 2 times per year you mentioned insults my intelligence periodically. Ouch. Also, I'm at the edge of my time zone, so my sidereal time is 0.5 hours, different from the average value of my civil time zone.
Okay. Yeah. Or somebody else said they're in Arizona and they don't go to daylight savings time, so the computers are constantly changing, their clock unexpectedly, and then all of a sudden they have to figure out how to make it go back. So that's another local problem you got to be aware of.
All right.
Okay.
From Blair, well done. From Audrey and Jack McElroy, thanks for the great presentation. Arthur, thanks a lot, great presentation. Jack Lobinger, how have you dealt with the problem of system calibration?
As in noise calibration, the noise source is the way that I've done it. I've injected that into the front end so that it adds a noise spike that's a calibrated amount. That's pretty much the way Green Bank does it too. They couple it into the signal path so that it doesn't vary with VSWR or anything. It's very, very stable. But you have to know what your noise source power level is to use that.
Okay, from Bruce Randall, after 25 years of radio astronomy, I still move the antenna with a pipe wrench. It works. And
Yeah.
he's not the only one.
Yeah. I have to say, people that go and try to install tracking, that is a major step. Drift scanning is definitely where most of the members are at. As soon as you go into tracking, you've got all the issues of what if you lose calibration, then the antenna drives itself into the ground or bends some metal part. You got to have all the emergency stop type issues taken care of. And so there's a whole discussion of how you do that first in software and then in hardware to make sure you don't destroy something just because a wire comes loose or a switch gets water in it. Okay, I see Dennis is putting on his SARA mask, so he's in pandemic mode. Okay, is that it, Richard?
Well,
I think we're done.
That is an outstanding brief. Thank you very much, Charles. And you're getting a lot of good kudos on the chat. Really appreciate all your work. Thank you very much.
And the 2 pictures that I've got up now, I'll have to credit my wife on those. She was helping take the astronomy picture here with a Fuji S1 and my 10-inch Meade of Orion, the trapezium. And then the one on the left she took as a time exposure where I was working at Perry with the antenna lit up by just a little bit of light from inside the building.
Great.
All right.
All right. Thank you very much. And
Okay. Stop share.
Yeah, go ahead. And Dennis, I guess you're selling those, Dennis, but I didn't put them on the raffle list.
No. I had one of these made up. My daughter-in-law makes them custom, and I just wanted to get in the spirit of the day.
Oh, that's the spirit of the day. Okay.
Well, that's why we're here instead of there. I would like to make one announcement. I would like to welcome Rosalind, I believe it's Daka or Dhaka, to our our Zoom conference. Rosalind gets the Distance Award. She's from South Africa.
All right.
Hello, everybody. Thank you for the introduction, Dennis.
Great. I think you're working with the SKA down there.
Yes, I am. And I was at the SARA conference in 2016.
Nice, nice. Well, glad to have you on board.
Thank you very much, Richard.
All right. Okay. We have one more presenter before the break, and so as soon as he finishes, don't jump off because I'm going to run the raffle. And if you're running to the bathroom during the raffle and I call your name, then I may have to choose somebody else. So don't quite run off. I'll do it really quick. Then there's a break, and then we'll go. Okay. Our next presenter is Steve Zekas, SARA member since 2013. He is an engineer and is currently on the SARA Board of Directors. Steve oversees the SARA account for the remotely operated 20-meter radio telescope at the Green Bank Observatory and provides a demo of it annually, which includes some technical aspects related to it. This year we'll be discussing the 20-meter output charge for pulsar observing. Steve, go ahead.
All right, thank you, Rich, for that introduction. So this presentation is given on the Sunday evening of the regular SARA GBO conference, and it's an opportunity to show first-time attendees that they have access to a large 20-meter professional radio telescope. And during the memo, we input the target and watch the telescope outside, move to the target and observe it. So this presentation is also posted in addition to the conference proceedings on the SARA Analytical Section website. If you're a SARA member, and here's the key, if you're a US citizen, that's a requirement for the NSF grant, you can get in contact with me and I can share the password with you. The only other requirement is you answer a few questions, promising not to do certain things with the radio telescope. So what I'm going to do is I'm going to share my screen, and I think instead of toggling back and forth between a PowerPoint and the website, I'm just going to go to the website first, the robotic Skynet 20-meter telescopic input screen, and then I'm going to go to the PowerPoint. So let me do that now. Share screen. Oh, here it is, share. Okay, and I'm going to bring up. So what you should see, if you can confirm that with me, you should see a page called Skynet Robotic Telescope Network, and you should be able to see my pointer because I'm going to be using that in this. Could you confirm that, maybe, Rich? That's what's up on the screen?
Yep, she's fine. Okay,
great. So I'll spend about 15 minutes on the robotic telescope and then the other 15 minutes on the PowerPoint. So you can get to the site Googling Skynet UNC, that stands for University of North Carolina. And after you input the password, you're going to come to a screen like this. And what you want to do is, it is very, very easy to use. The inputs are very easy. You can't break this. No matter what inputs you use and where you point it to, you will get an output. The challenge to this is understanding what your output is and getting better with time on it. So we'll look at some of that. So up on my observatory, there's an optical and radio option. SARA has the radio option. And we're going to click that. And you're going to come to this screen. And this is a listing of observations by SARA members. And we'll come back to this a bit, but this is a hyperlink where we can actually see the observations. And what we want to do is, since we're in radio observations, we want to add a new observation. And you have a couple choices here. You could go to the hemisphere here and pick out an item and it'll populate, or you can add one yourself. And since my presentation, the PowerPoint later is going to talk about the pulsar output when using the 20 meters, I'm just going to put in Taurus A, and let me correct the spelling. And it found it, supernova remnant pulsar. It pre-populates some of this. You can change this, but we'll leave it in there for simplicity. It shows when it's visible here, and we're going to save and continue. And then you'll come to a screen like this. This is where you have some options, whether to stay with low resolution or high resolution. For pulsar mode, it's in low resolution, so we'll stay on this screen and we'll check mark the pulsar box. And then we'll continue and save. You'll get another screen. For pulsar, we'll leave it right where it is. But if you weren't doing pulsar mode observation, you do have some other options here. Map, Daisy. Daisy is a sort of a partial map. And on-off, which is similar to tracking, except that it looks, it tracks and then looks a degree or so off just to get a background comparison and make it a little bit of a tighter observation. For a bright pulsar, you might want to use 60 seconds, but just for the demo, I'm just going to put 1 second. Continue and save. You get a summary of what your input variables were. There's a box that shows the balance in the account. These credits mean seconds, so I've used 1 second if I were to submit. There's no queue for, usually there's no queue for the 20 meter scope. You click this, you should get a couple minutes later the results. At this time at Green Bank, we would just walk outside and wait for the radio dish to start moving and record the observation. We're not going to do that here. I'm going to show you some previous observations. But as simple as that, if you're a beginner, I would suggest putting in a small amount of credits so you don't eat up the balance in the account. The raster scans consume a lot. They're about a 25-minute minimum. So a couple of those can break the budget, but there's plenty of examples. If you do want to do a raster scan for something, let us know. I mean, I could discuss it with the SARA leadership, and usually we'll ask you, well, can you write us an article on what you were investigating? So let's go back now to the first page that I was on. I want to show you what the results look like. So I'm going to select this one. This was Cassiopeia A. It's a raster scan map. And when you look at the results, you'll come to a page like this. It'll summarize what the observation was. And then you'll want to click the link to the Radio Astronomy Observatory at Green Bank. And you're going to see what it is here. So this is the raster map, two-dimensional depiction of Cassiopeia A. A lot of information here. You've got a couple of different modes, and this is on the B, but you can switch to the butterfly symbol, and it provides some data here. And there's a few key things in here I think are very important. If you want to operate if you want to understand how to operate, this link here, 20 meter info, is very good. It gives you a lot of documentation. There's no help desk for the 20 meters, so this is an important place to review the materials that you're that you could read for your observation. And this link here, 20 meter documents and memos. Additional here, including some calibration documents, which I found useful. That's where you got a lot of documentation for it. back here, if you want to see the raw data that went into it, you can click the raw ASCII. On top, you'll have the input parameters and then the data. And if you want to see the calibrated data, it looks similar, but it is calibrated, and you could use this data to calculate flux values. So last year, what I like to do every year with the demo, because the demo is fairly easy to go into this website and show that you can input parameters and get results. I'd like to focus on some aspect of the results of the 20 meters. So the last couple of years I've been doing the variable radio targets like Cassiopeia A. Could we use something that varies as a citizen science database as a basis for that? So last year, and if you want to look at that PowerPoint, that's also on the SARA analytical section under CASA observation program. And that PowerPoint shows how you can use a 20 meter to calculate a flux value. This year, I'm going to be looking into the pulsar output. That was something new for me, so I wanted to understand that. And then the other important thing here is you'll see a log here. You want to click that. And here's a log of not only SARA observations, but everybody who uses this robotic telescopes. Starts here, and it goes back to 2013. And in this is it varies a lot as far as the quality. Some of it is student data, some of it is first-time folks who just went on and didn't read the instructions and just wanted to see the output, so it's not very good. And others is professional observations. If you want to see a pulsar output, usually you'll go to something that says PSR, Pulsating Source of Radio, or PSC, Pulsar Search Collaboratory. We can click onto one of these. For pulsars, you'll get an output that looks like this. And the PowerPoint portion of my presentation is going to explain what this is within about 15 minutes. This is called a prep fold plot. And in the prep fold plot, there's 7 main panels. You've got on the left, you've got 2 here. In the middle, you have 2. On the right, you've got 2. Here's the other one. And the 7th is the search information. So we're going to look at that, because there's a lot of information there, and unless somebody explained it to you, you know, maybe it's not going to make much sense if you select pulsar mode. And looking at the proceedings, I've noticed there's 2 other presenters who make use of the prep fold plot in their presentations. So I guess this was timely. And again, so if you're new, you can go in here and look at other people's observations. And you can do a search to see, you know, sun, moon, different deep sky objects, and get a feel for what people put in there, as well as your own. All right. So at this point, I'm going to now switch over to my PowerPoint presentation. And Rich, can you confirm to me that you're seeing the PowerPoint presentation?
I do, and I had a couple questions real quick before you shift to this. Okay. From Tom Aslan. One is, how do I get a password for this, and what's your contact info?
All right, so you're going to get a password by emailing me, and my email information is at the end of this PowerPoint presentation. I've got 2 email addresses. You can also find my email address in the SARA section's analytical section. I'm the coordinator there, so I've got my email listed. I'm also one of the directors, so if you go to the management page on the SARA website, you'll also see my email there. So that's the easiest way. And the restricting item is you got to be a U.S. citizen. We don't have control over that, but otherwise it's 2 or 3 simple questions. You've got to agree to that, and you're in. So continuing on with the PowerPoint. Now this is 46 slides, so I'm not going to go through each one. I'm going to select some highlights because I don't have a lot of time. Normally when I do this is maybe about an hour and a half in the evening, so I kind of combine it with an analytical section meeting and talk about what can we do with the 20 meter, what are some projects, as well as demo it, and have some discussions. So agenda, I'm not gonna spend too much time on these. You can read them, talking about the account. There are other ways to get this account. You can go to Skynet University, and there's a free UNC course on Skynet. They give you an account. I'm not sure if that's both the optical and radio, but it's definitely the optical. And some some astronomy clubs have the 20 meter as an option where they allow their members to use that. Just to summarize, these are some of the snapshots of where we just were on the 20 meter site. Depending on what you pick, if you were to take high resolution, you might get a, you will get the pop-up for this to select your primary and secondary frequencies for hydrogen line observation. You can also do hydroxyl observation, which are useful for MESARs. Some information on Pulsar Search Collaboratory gives you some training materials, very useful. On this page, I think it's probably useful to point out that pulsars do have a naming convention. You'll see if it's not a common name like Tara say that I put in, you'll see a long alphanumeric name. It'll start with a B for Besselian epoch, which starts from 1950, or a J, which is Julian epoch, that is updated for 2000. And then right after that is the right ascension and declination. So that's how pulsars are named. And here's a few tips on what input parameters you could use. I mean, I had 1 second in there, but if it's a bright pulsar, you want to maybe use 60 seconds. For a listing of pulsars, you can go to this website, which is the Australian equivalent of the NRAO in the US. They've got a pretty good listing. And I like to say something about the folding process, because this Presto software makes use of that. So a noise that's inherent in instruments makes a single pulse very difficult to see. In order to solve this, astronomers must fold many pulses together in order to build up a detectable signal. So I guess the equivalent of this in the optical astronomy world is stacking of the photographs. Another thing that's important to mention is Fourier transforms. If you read enough radio astronomy, you'll come across this term. So Fourier transforms are mathematical operations that are very suited for finding repeating signals in a set of data. And so for pulsar searches, the transformation takes data that's in the form of a signal versus time and converts it to signal versus frequency. And both are related because frequency is 1 over time. So that's an important point to know. I mentioned harmonics and radio frequency interference, but I'm not going to spend too much time on that. You can read it. And this is the chart that I want to spend a little time on, and a few next slides that break this down. So Presto is the software that creates this, and the PrepFo plot is the chart you're looking at on the right. And there's 7 panels. As I noted, there's on the left, there's 2, 1, 2, 2 in the middle, and on the right, there's 2, and the 7th is up here. So this is the time series and pulse profile on the left, and I'm going to start off with those. So this one in particular is the time series, which represents the strength of the signal as a function of phase and time. The pulse profile, that's going to be the folded signal of the pulsar that was collected over the entire observation. You'll see that it's made up of gray squares. Each represents the strength of the signal and some small piece of data called a bin. And these separate panels starts off on the left, which are easier to comprehend. As it goes to the right, gets a little more difficult. But, you know, think about these slides when you read them later, and I think it'll make sense. Here's the pulse profile panel. It shows the strength of the pulse as a function of phase. And then we're coming to the two middle panels. I'm sorry, I'm kind of going through this quick because we've got about 10 minutes left, but I think I can make my points here. This panel shows the strength of the signal as a function of both phase and frequency. Again, the darker bins means that we've detected a stronger signal. Each gray bin in this image represents the power collected in a single subband over the full observation. And now we're going to come to the other middle panel. It's the dispersion measure panel. So DM stands for dispersion measure. The dispersion measure tells us something about the space between Earth and the pulsar. That space is not empty. The electrons is one of the things in that space, and it scatters a signal from the pulsar. The other axis is the reduced chi-square. That's a statistical value that indicates how well a model agrees with some actual data. And normally in mathematics, a large value of reduced chi-square means that the model and the data are not in good agreement, whereas a reduced chi-square of 1 means that they are. But Presto uses this information in a very uncommon way because we don't know of the properties of the pulsar ahead of time. When we compare the pulsarless model to the data that does contain the pulsar, we see a high reduced square. And that's exactly what we want to see. So if the curve reaches its highest point at a DM of 0, then the signal must not have traveled through any electrons to get to Earth. That means this peak is over at 0. It's very likely to be radio frequency interference. So the dispersion measure is a way of quantifying the number of electrons that the pulsar signal must pass through. And a real pulsar should have a peak value of reduced chi at a non-zero dm. Now we're gonna go to the left two panels, the right side of the prep-fold plot. And you're gonna see two panels that look similar to the dispersion measure plot. They're stacked one on top of the other, each other rather than side by side. And they have the reduced chi on the y-axis. And these are the period and p dot charts, and they have a number subtracted from them from the bottom. You'll see that here. It's subtracted so we can easily see how far the peak of the curve is from the central value. So the p dot, or period derivative, is the first derivative of the period. It shows how much the period is changing over time. And generally speaking, pulsars ought to be slowing down. So when determining whether a candidate is a true pulsar or whether it's just radio frequency interference, you should look for a sharp peak in the reduced chi versus p dot curve. You should look at that for some additional information. So isolated pulsars typically have a p dot that's too small to measure in a short observation, and hence it appears to be 0. And then the last panel on the right is the period of frequency and p dot, f dot panel. These are the previous two plots put together. In this case, the colors represent the reduced chi-square, the red meaning a high reduced chi-square, which is what we want, and the red would correspond to the peaks. So in this panel, you have the period and period dot are on the x and y axis, and the reduced chi-square is represented by the different colors. Remember, the frequency is essentially 1 divided by the period. So think about these, read them a little later on your own, and they should make sense. the last part is the search information panel. That tells you a little bit about what you're viewing. That's this up here. There's a lot of terms in here. So at the end of this PowerPoint, I've got a glossary of general radio astronomy terms, but there's also a glossary of Presto terms. So all of these are explained. All of these terms are explained in that glossary. All right. This also represents an example of, this chart here represents an example of a radio frequency interference. So notice that right in the pulsar profile, the pulse profile chart, it's not sharp peaks, they're rather broad. That's a giveaway, it's radio interference. Notice too that in the dispersion measure plot, you have, it's at 0, so it really didn't travel far. And we've got some examples. I know we're coming up to the end of the half an hour. This is an example of a binary pulsar. Signals tend to drift in phase. Here's an example of another type of radio frequency interference. Real pulsars don't abruptly jump in phase. Notice that the dispersion measure chart is flat. Normally we want to see a peak there. And notice that the period is almost 3.3. My PowerPoint is blocked by the participant boxes, but right in this area, you'll see that the period is 3.3. That corresponds to a spin frequency of exactly 300 hertz. So that's obviously man-made, so that's a giveaway. Give a little bit about narrowband and broadband signals, as well as transient emission, eclipsing pulsars. Again, all this is taken from a document by Ryan Lynch, Pulsar Search Collaboratory Guide, searching for and identifying pulsars. You can read that on the internet. It's posted in several spots. It gives a little more information on how to use Presto and the prepfold plots and what they mean. Again, Ryan Lynch is searching for and identifying pulsars. I'm going to speed up a bit. Transient eclipsing pulsars, column density, signal conveniences. Here's the general summary of steps for identifying a potential pulsar, the 20 meter. We have a general glossary of radio astronomy. I've got some other examples in here that you can look at, and you can try to determine if this is a real pulsar or radio frequency interference. I'd probably like to also point out that if you want to see the actual data for this, notice that there is a date right here that allows you to go into that master log on the 20 meter, scroll to October 19th, 2019. There may be one observation, there may be several, but then you also have the name of the observation here. So you can go into the actual record of this and look at it. So this is just a snap of it, but you can actually go in and go to that data for more information. So that's very helpful. Especially if you're learning this, you want to look at what others have done and what they did for input parameters. So here's the glossary of the Presto terms. There's quite a few of them there. If you want to know more about Presto, you can go to these links right here. I've enjoyed working with the 20 meter. When I first went on, I was experimenting with it. I really didn't know much. And as time went on, I got better and better at it. It's very easy to use. The challenge, I'll say again, is understanding what you have. You can point that 20 meter anywhere in the sky and you'll have results. And results can be misleading. You You can point to Pluto and you'll get a hydrogen line reading, but it's not really Pluto that you're looking at. It's the hydrogen behind Pluto. So you've got to understand what you're doing. Here are some applications. Next year, I'm planning to do astronomical masers. That seemed of interest to me. I know the 20 meter can record them because I've tried that in the past. I did get small signals, so I want to improve upon that and demo that next year. Some of this I've posted on the analytical section, so there's a guide there on radio occultations. You can look at that. That's on the SARA analytical section. And here's my email. I put two. The RPI address is, sometimes that has filters on there. It might block you, but definitely the Gmail is easy to get through. And you'll see this also posted on the SARA website. I'm going to be also in the Drake Lounge, a virtual Drake Lounge tonight, so you can catch me there for questions. And Rich, do we have time for questions?
Go ahead, I have a few questions.
All right. And maybe I'm going to stop sharing so I can see the chat room as well.
Yeah, I'm not seeing any more questions on chat.
All right. Well, as said, I'll be available throughout the conference by email, the chat, or virtual Drake's Lounge.
I got
And
one
if
from.
you're interested in trying the 20 meter, just email me for the password and we can get you set up on that.
I got one from David Fields. Will NRAO be supporting another instrument for amateurs?
Well, NRAO will, even though the 20 meters on their property, they're going to tell you that it's operated by Skynet, which is out of University of North Carolina. Dan Reichert's the contact there. He was our keynote speaker, I think, in 2013, which is my first year at Skynet. So they're the overseers of that. Although NRAO does have some input, a lot of the documents for that come from NRAO. So, and for our SARA account on the radio, we purchased that through Green Bank GBO, which is the new name for the NRO facility there in Green Bank. I don't know what their future plans are. They have a very active outreach. I mean, we hold our conference there every July or August, but they host a lot of other groups there. They have a lot of student groups that come in. They have training exercises at Pulsar Search Collaboratory. I don't know too much about that, but I think they're involved there. They do some training. So they're very active with that. I don't know about other instruments, though, if they have anything planned. One of the things that SARA management is looking into, it's in disrepair, but we brought this up with Green Bank. There's a very large radio astronomy horn on their property, and we're hoping that can be refurbished and brought back to life. So maybe that's something for the future. And that was used, I think, back in the 60s for Cassiopeia A observing.
Okay.
Can I just put a quick comment in for the 40-foot?
Go ahead.
Sorry, to answer that question, yeah, if you have an educational group, certainly contact Sue and Heatherly, or me, and you know, we'll arrange something with a 40-foot.
And this is Skip Crilly talking.
Yeah, thanks.
Yeah. Okay, last I got from Aubrey and Jack McElroy and their family. Wow, a very cool presentation. Nice job. From David Fields, thanks, Stephen. This horn is awesome, though, in some disrepair. All right. Yes, it
That's
is.
a good point about that's a good point about the 40-foot, because there is a workshop, and Skip oversees that, and it is available 24 hours once you're there. So if you do attend the Green Bank version of the SARA conference, I mean, you need some sleep, but if you want to stay up throughout the night, you've got the 40-foot, you've got a very dark sky there for optical observing if you bring your telescope. Of course, the Drake Lounge is a great place for a lot of conversation on radio astronomy. So thank you.
All right, excellent. And stand by. I just did the, trying to find it here. What did I do with it? Door prizes. Okay. I've got, oops, sorry, wrong door prize. I thought I had my door prize thing up. Yeah, there are the two winners. I've got Virginia Wiley and Paul Cernosky. And stand by while I get my share up here and show you the prizes we got. I think that's it. No. There it is. Okay. So Virginia Wiley, are you online? Oh, Paul Cernotsky, are you online? Wow, our first two. Okay. I'm going to make two. I'm going to choose two other ones. This is the problem if you're not online when we call your name. All right, number 69 is okay, James Van Pruin. Are you online? You guys got your audio muted. You got to unmute your audio to talk, or text me that you're there. Okay, well, this isn't working as well. I thought we'd get more. Oh, wait, who's that?
Jim Van Bruin's here.
Who is? Yay! All right. Here's your options. If you can see that running total side. What prize would you like?
Oh, hold on, I gotta go back to that if I can get the right options here. The signal generator would be extremely useful.
Okay. Hey, if you could send me a chat or an email with information on it, your address and everything, that'd be wonderful.
Yep, I'll do that shortly.
And congratulations, that was the number one. Okay, I got one more, and let me call them again. Virginia Wiley, Paul Cernotsky. You guys online?
Hi, this is
okay. I'll make another.
This is Virginia.
Oh, okay, great. Would you guys like which? If you look at the screen, which item would you like?
Is the Super SID still available?
Absolutely.
We'll go with that one. I was just online trying to see if they had any available, and they look like they're getting pretty short.
All right. Okay, you send me an email with your information on it, your address and everything, and we'll get it to you.
Will do. Thanks so much.
Thank you. All right, that's our two for this break. We are going to reconvene at 10:45 with Wolfgang Herman's excellent brief on the Osterpeeler 25-meter radio telescope. So take a break, and we'll be back in it shortly.